First of all, thank you for inviting me. This presentation begins the definition of near-planarity. The near-planarity is if there is a planarizing edge, or G consists of just isolated vertices. So following this definition, every planar graph is also nearly planar. So I want to make a bigger class of the graphs than the class of the planar graphs. But the sad thing is that minor of nearly planar graph may not be nearly planar. So in this graph, there's a planarizing edge in here, right? If I delete this edge, then it becomes planar graph. But if I contract this edge, then this is not a nearly planar graph. However, every topological minor of a nearly planar graph is a nearly planar. So we can use topological minor, but we cannot use graph minor properties. Among the Bogdan-Opolowski academic brothers, if we use type 0 and type 1, we can build really big non-nearly planar, minimally non-nearly planar on the topological minor. And I add type 2. And the type 1 and type 2, these two are actually made by a pair of type 0. So what I'm saying is that a pair of type 0, if two subdivisions of two edges share a point, then it becomes type 1. Yeah, I will subdivide one of each of type 0. And if a subdivided edge share among these subdivided edges, and these two new bodies are identified, then it becomes type 1. And type 2 is made by identifying edges of the subdivisions of each pair. So what I'm saying is that if I subdivide one side like this, and this side also like this, and identifying these two edges, then it becomes type 2. This property is used for minimality of non-nearly planar. So what I'm saying is that on the projective planar, I will make boxes, and each box I will put type 0 or type 1 or type 2. So it's type 1, just one side type 0, and the bottom is not used, so I will contract the bottom. And I can use type 2, and I can use type 2 consecutively, and a pair of type 0, and so on. If you want a big, minimally non-nearly planar, then you can use lots of boxes. And I said minimal, and it's not nearly planar. So what I'm saying is that whatever you choose on edge to delete, then after deleting that edge, it is still not planar. But I can choose the second edge to make planar after deleting. And it depends on the property of the parallel edge. So if you choose this edge to delete, and I can select this edge or this edge, because this edge is made by just identification of subdivision of edges, right? If you select this edge, then I will select this edge to make planar. So I want to destroy the parallel edge structure. So you can believe that if there are lots of boxes, then you can use just type 0, type 1, and type 2, and you can make minimally non-nearly planar graphs as big as you want. So the next question is that, is this only way to construct the big minimal non-nearly planar?
So why is it not
Minimal, yeah. Minimally not nearly planar. So minimal, yeah, yeah. There are lots of English, yeah. The meaningful English words. So it's not nearly planar, and it's minimal. So what I'm saying is that if I delete any edge, then it becomes, after deleting any edge, it becomes nearly planar. Because I broke the minimality from the deletion.
So basically in the picture, the graph you get is like you identify these two alpha.
You're right. So I said,
But there are no other edges, like from top to bottom.
you're right. You're right. As you said, these two arcs is just showing that the projective plane. So on the projective plane, I can draw the minimally non-linear planar without crossing. So just I want to show the graphs without crossing, so I use the projective planar. So that's the reason the beginning is, yeah, the setting of the projective planar. Yeah, I need to say that, but I skipped. Yeah, I'm sorry that. So after identifying these two arcs, you can get projective plane, right? Yep. But you may notice that using type 0, so what I'm saying is that using, if you see this bottom of a pair of parallel edges, and you can change the given the bottom parallel edge like this, a series of parallel edges. So I can define this action is a parallel subdivision. It looks like subdivision, but it's different from the original subdivision. If you use this parallel subdivision, then you can make a sequence of minimally non-nearly planar graphs on the topological minor, right? It's minimal non-nearly planar, both of them under the meaning of under the topological minor relation. So if you delete any edge, then I will delete the other edge. The other edge means the other parallel edge. Then it becomes planar graph. So it's minimally non-nearly planar graphs under the topological minor. But the sad thing is, we can build infinite sequence of parallel, minimally non-nearly planar graphs using parallel subdivision. So I want to delete this. I want to omit this parallel subdivision. So I want to define a new relation. So the first three is actually related with topological minor. The new thing is just parallel unsubdividing. That means I do not allow the parallel subdivision. So H is a new subgraph of a new relation of G that is made by these four. So we want to get a simple list of minimally non-nearly planar graphs. So it's too long words, so we will define the class M as the class of graphs under the new relation, minimal non-nearly planar graphs. The class M contains K34 and K6 minus 1 edge, Peterson graph, and double-edged K33 and double-edged K5. Professor Oprovsky and I checked that in this class M, there are 3 disconnected graphs, 10 connectivity 1 graphs, and 57 connectivity 2 graphs. So next thing is 3 connected graphs. So to deal three connected graphs, I will use the result made by Professor Ding, Gorley Ding, Bogdan Rofsky, Robin Thomas, and Doug Vertigan. To use their result, I want to define the definition T-shallow. In T-shallow, in this definition, they said separation of order n most 3. They said that, but it is enough to just focus on separation of order 3 because I cleared the separation of order 1, order 2 in the previous paper, presentation. So you don't have to worry about the separation of order 1 and order 2. So they define T-shallow in separation of order 3. One side must be embedded in a disk, and the size of that side must less than T vertices. So I will explain this meaning later. And using this T-shallow definition, they made a theorem that depending on two integers, there is an integer n. So this n is a function of two variables k and t. Every three connected T-shallow non-planar graph with at least n vertices contains bk, nk, k for k, and k for k prime as a topological minor. So this result is related with the topological minor, so I can adopt their result in my research.
What does this G bar A mean?
The graph is restricted in the separation A.
So is A a subset of vertices or?
Yeah, subset of vertices. So yeah.
I don't understand the induced graph on the vertices A.
Yeah, so I will explain the later part. So in this case, in this graph, we can these three are separation of order 3, and these three vertices are included in the vertex at A and vertex at B simultaneously. And after that, we may assume that G restricted in B has a topological minor of CLO, because we are talking about just three connected graphs. So we may assume that G restricted A with CLO. So
do you assume that B is the part which has the most T vertices?
I will say it later. So you don't have to think about that right now. So now we don't have to think about the size of A and the size of B. Just we are thinking about the structure of A and structure B. And we are talking about just a three connected graph. So in the B part, B side has a CLO as a topological minor. If yes, no. If G restricted A, this induced subgraph cannot be drawn without crossing in this disk, then means G restricted A contains K23 as a topological minor. You may notice that the other G restricted B has CLO. So because of that CLO, A part has K23. Or you may think that the K5, but K5 has also K23 as a topological minor. So G restricted A must have K23 as a topological minor. Actually, one of these four. So I said that we want a T-shallow argument. So one of these parts, so because of that, I want to avoid K34 as a minor. Right? If G restrict A and G restrict B have K23 as a topological minor simultaneously, it means K34 is a minor of G. So because of that, I want to avoid K34 as a minor. So after this presentation, from now, I will eliminate K34 as a minor from G. So if K34 is not a minor of a graph G, then exactly one of G restrict A and G restrict B can be drawn in a disk without crossing. And by the minimality, the kind of a planar part of this separation has almost 9 vertices. So now we can say that the graphs in the class M is 9 shallow. Because I eliminate the K34 minor. And because of K34 minor argument in the previous thing here, K4K and K4K prime, these two are also eliminated. And I need to say the definition of K4K prime. And what's the meaning of K4K prime is that I want to give an example from K34. K34. And you want to split degree 4 vertices. And you can choose. So you can select if you split this vertex in this way, then the other 2 vertices also must be split in the same direction. This is the definition of K4K prime. So split the degree 4 vertices in the same way. But yes.
So I have a question. So here,
Yeah.
If you have a bounded, if you have a T-shallow graph,
Yeah.
you might simply take a claw inside the planar part.
Yeah.
Because graph is
You are right.
and then you basically reduce the problem into 3 connected graph, but actually the all 3 cuts have only one vertex, one internal vertex on the left hand side. And it's more like if you prove something like this for internally 4 connected graph.
You are right. Yeah.
So
Yeah, internally 4 connected is so actually T-shallow, the definition T-shallow is checking all the 3 separation. In your case, internal that means internally 4 connected means the shallow is 1 shallow, right?
yeah.
But in that case, 1 shallow is
Shallow is something.
you are right. 4 shallow. Sorry, you are right. 4 shallow. 4 shallow is included in 9 shallow because the definition is just fewer than T. Yeah. So 9 shallow is included in the 9 shallow graph is included in the class of 9 shallow. So yeah, you don't have to worry about that by the definition. So we are just talking about the bigger class. And by the definition, if the connectivity is greater than 3, then we assume that the shallow is the connectivity is greater than 3, then we assume that that graph is called every number shallow. So, yeah. The assumption is false, so we can say everything, by the logic, mathematical logic, So 9 shallow is fine, and because of this K3 for elimination, K3 for minor elimination, the bottom two, K for K and K for K prime, are eliminated. So this Ding, Oprovsky, Goli Ding, Bogdan Oprovsky, and Robin Thomas and Doug Vertigan's result is reformulated like this. Just we can focus on BK and MK. So now I want to explain the definition of BK and definition of MK. Before that, I want to say the number of K, and for my convenience, I will set K is 20. This is not optimized. Bogdan Oprovsky says that set the number as I want. So I set number 20 for the convenience of calculating. So I set K20, and this number is coming from 1993, Bogdan Oprovsky and James Oxley and Robin Thomas. And this K is also 20. I need to type the number 20 in here. And this 20 is actually the same, the K, number K in here. So BK and MK. BK is coming from alternating double wheel, and we add on axle, so it becomes nearly planar graphs. And in the subdivision of BK, we will add more axes and vertices to make not nearly planar graphs. But when K is greater than 9, K is the number of spokes. Then there are lots of spokes to become minimal. So what I'm saying is that if a graph G contains subdivision of BK, when K is greater than 9, then the graph cannot be in the class N. It's too many spokes. So BK is eliminated. And Möbius ladder. If you delete rematch, then it becomes planar. But if you delete the wrong edge, then it is still not planar. So because of that, in this Möbius ladder structure, we will add lots of more bridges and we will add more edges and vertices. But I tried, but I failed. So because of that, in the beginning of this presentation, I explained that only we can use these three types on the projective plane, and using these three, we can construct the class M members. And this is the only way, only way to make the big graphs in the class M. So, except finitely many graphs, finite, but the finite number is really big, but except that finitely many graphs, we know the structure of the graphs that are minimally non-nearly planar graphs. That is depending on, those are depending on the Möbius ladder structure. Yes?
I missed how you construct all the members of N.
Members of N, the construction of members of order N, the class N is this one. And that is the only way to construct really big, minimally non-nearly planar graphs.
So basically, you have a big.
Yeah, big Möbius ladder structure. Yeah.
You identify these two, and
Yeah, you are right.
replace each box.
You are right. Yep. And this is my PhD thesis paper. And the next step is we want to get a bigger class, which is closed under minor, graph minors. That's the next step. So Professor Golding and I declare a class that a graph satisfying one of these two conditions. So the first one is just a nearly planar graph. And this first one is just depending on edge deletion. But the second one is we find a bigger set G prime such with an edge E, so it's a planarizing edge E, such that G prime contraction E is isomorphic to graph G. So from the graph G, we find the apex vertex, and we will try split that apex vertex in different ways. And after splition, if the new edge becomes planarizing edge, then I will put that graph, original graph, to the class E. Fortunately, this class is a minor closed class. But sad thing is that Professor Golding find the equivalent class of graphs. What the meaning is that the spindle surface embeddable graphs. Yeah, spindle surface is a pinched surface formed by identifying 2 points. What I'm saying is that is, yeah. In S2, identify north pole and south pole. North pole and south pole. And after identifying 2 points, you can get weird surface. Actually, this is not a surface. It's a pseudo surface. And Professor Golding and I proved that actually class E, every member of class E can be embedded on the spindle surface, and a graph G can be embedded on the spindle surface means G is a member of class E.
Is this non-trivial or is it?
It's actually trivial. I can explain that in using short time. So if it is planar graphs, then it's done. Just I will draw the planar part in here. Yep, the problem is nearly planar situation. So if this is planarizing edge, then after delete this edge, we can embed the graph on the plane. And after that, it's weird, but you can put like this line segment on the embedding, planar embedding, and identify these 2 points. Then the other planar graphs can be embedded on the spindle surface. And this critical point contains actually lying on the planarizing edge. G prime planar is isomorphic to G. Yeah, in this graph G, the second condition, in this case, I will set G prime minus E. Yeah, you can draw G prime minus E on the plane, and after that you can identify two endpoints of the deleted edge. Then this critical point is containing the edge, the point made by edge contraction. Right? The new vertex made by this edge contraction is relying on the critical point of this spindle surface. And the reverse action is actually the same. So, even though I said the spindle surface embeddable graphs, but I will use the edge deletion and edge contraction. Because edge deletion and edge contraction is commutative. These two actions are commutative, so it's easier to handle. And I want to explain Dan Archdeacon and Bonington's result. They restrict the situation just only on cubic graphs. So they ignore other graphs. So the universal graph set is just cubic graphs. So because of that, we cannot use graph minors. If you construct graph minors, if you construct on edge, then the new vertex has a degree more than 3. So they use just a weird topological minor. After edge deletion, there are 2 degree 2 vertices, and you can unsubdivide these degree 2 vertices. Then it's still the new graph becomes the another cubic graph. So the universal set is cubic graphs. And in this situation, the minimally non-spindle graphs and minimally non-nearly planars are actually the same condition.
So by minimal, what?
Minimal is, in this case, yeah.
On one side you have a minor, and on the other side you have only deletion of edges?
Yeah, because in cubic graphs, I said that universal set is cubic graphs. Yeah. Yeah, but because of that, we cannot use edge contraction.
So the operation that you do is deleting an edge?
Yeah, and after you can smooth the degree 2 vertices.
I see.
So it's a kind of weird topological minor relation, right? But they restrict the universal set just on cubic graphs, so they are just focusing on just edge deletion. And they said that there are 21 minimally non-nearly planar graphs. This means there are only 21 minimal non-spindle graphs in these cubic graphs. And to find these 21 graphs, Archdeacon and Bonington said that they use computers and they checked by hand. After reviewing their result, Professor Goli Ding and I find that the projective planarity does not help to find the spindle surface obstruction. So Peterson graph and this graph can be embedded in the projective plane, but these two are not. It's so sad. But Archdeacon and Bonington shows a reference that Bodendieck, I cannot say his name, and Wagner's conjecture. They define a new relation. So H is dominated by G. That means H is made by these 5 sequences, 5 operations. And these first 3 are easy, right? Vertex deletion, edge deletion, and edge contraction. And you may hear Y delta transform if you studied the Peterson family. And they showed a new relation, double Y double delta transform. They in their paper they said double trihedral transform, but yeah, it's actually similar to Y delta transform. I will show this fifth the action, right? Yep, you know K to 3, and there's a Y in red edges, and change this Y form claw to triangle. This is Y delta transform. And in Wagner's paper, delta Y transform is not allowed. Just Y delta transform is allowed. And double Y double delta transform is that there's kind of double Y. In original paper, is the double trihedral, and this is changed to 2 triangles. So K33 becomes K5 using this transform. Let S be, this is German letter S. G is the class of minimal not spindle embeddable graphs in this relation, and they find 12 graphs in this class S. So direct sum of K5 and one sum of K5 and kind of 2 sum of K5, and one vertex is joined to K33, and this is actually K35 and K6, and these 6 are new graphs. And they made conjecture that these 12 are old. But this is conjecture 20 years old. Yeah, 20 years, 25 years, and this is still conjecture. But yeah, you know that we may guess that the total number of excluded minor of spindle surface is really small. We can guess that. So I tried to get excluded minor of a spindle surface, and in the viewpoint of connectivity 0, I find these 3, and connectivity 1, we can find these 3, and connectivity 2, we find these 6. And 3 connected minor obstruction, we are still finding the list. So we want to find the complete list of excluded minor of spindle surface. This is the end of my presentation.